Howdy folks, welcome back to another CS 120 honors lecture. In this lecture we're going to be talking more about structs and generics. And so generics are something you've seen in the past, we've sort of brushed over them. Anytime you have a vector or a result or an option and you use those little angle brackets, that is an example of generics. And so today we're going to formally introduce you to them and introduce you to how you can write your own code with generics. Okay. So we're going to briefly review methods on structs, because that will come in when we use generics. Then, formally introduce generics, and then talk about smart pointers and what those are and how they relate to generics, and eventually how they relate to linked lists. And if we have time, we'll cover linked lists. I believe we'll cover homework 8 hints next lecture, but generics and smart pointers will play in directly into homework 8, and perhaps the next lecture will give you a good start on completing homework 8. Okay, a couple of quick reminders. MP1 is due next week on the 27th at midnight. MP2 is releasing tomorrow. It's going to be due on March 8th, I believe, at midnight. If you need extensions on these, please reach out to Arul and myself. We have the 70% credit deadline built in. I believe the MP2 70% credit deadline runs into spring break. So we'll be moving it to like 2 weeks instead of just 1 week. So you have that adequate time and you're not working over spring break, hopefully. And yeah. Okay, let's get into it. So struct methods, very, very similar to normal functions, use the fn keyword. And these functions just contain code that's run somewhere else. However, they're sort of defined in the context of a struct, or an enum, or trait. Traits and enums, or rather, just traits, will come after spring break, but we'll be implementing custom methods on an enum today, but the same can be applied for structs because they have practically the same syntax. So you use an impl block, an impl keyword to define these methods that you're implementing for your custom type. And the first parameter is almost always some variation of a borrow on self. You're representing that you're borrowing the current instance of the struct that the method is being called upon. Very rarely are you actually taking ownership of self, so you should always have some type of ampersand in front. And yeah, so ampersand self, again, immutable borrow to the current instance. Ampersand mute self, mutable borrow to the current instance of whatever the method is being called upon. Again, this is from last lecture. Okay, and then we can use dot notation on self to access struct fields and call other struct methods within any method that has struct or self as a parameter. Okay, so generics. Generics allow you to generalize your types to broader cases. You've probably seen them in C++, you've probably seen them in almost every other language. You have a container of some type. Rather than writing a vector of ints and a separate class for a vector of strings, or a separate class for a vector of whatever the case may be, you just write one vector class and you generalize this type to all broader cases. So, like I just mentioned, they help in reducing this code duplication. You just have one implementation, and the compiler gives you all of these different implementations for free. So you get a vector of integers, vector of strings, all for free because we have the vector class. And so generic type parameters, or what they're called, are represented as these angle brackets and then some variable in here. So you'll see t a lot. I tend to use t to represent some type. As in the case of hash maps, you'll see a k for the key type and a v for the value type. It quite literally doesn't matter. This is just a variable that you'll see used throughout the code. This variable is a type. So generic type parameters describes anything that accepts one or more generic type parameters. So you can have one type parameter, two, like in hash map or result, and so on. So if a type is not generic, it is a concrete type. So concrete types are the ones you're familiar with, integers, strings, etc. Okay. So we've seen this before in option. You have option and angle brackets t. you've seen optional strings, optional integers, optional colors, all that. Same thing with results. You have a result with some success value of type T and some error value of type E. And, as is the case, we can put the unit type, just, an empty tuple. We can put integers, any other type within them. This T can expand to any type. We've seen a vector. You'll use hash sets, I believe, in MP2. And hash maps in MP3. So hash sets are this just collection of distinct elements of some type T. So they're unique elements of some type, and they're in this container. One thing to note is that there's no order to them. Hash sets don't give you any guarantee as to how they're ordered within. So be careful with that. Same thing with hash maps. It's like a dictionary, if you're familiar with that in Python. It's a collection of distinct keys of type K and their corresponding value. Okay. So in generics, you can pretty much template any piece of code. You can template custom types, so structs and enums. You can template your functions. You can make a normal function over a generic type. You've probably seen this with parse from MP0. You can parse into any integer type, a float, an int, unsigned int. You can, basically write code for free. And then you get these templated interfaces, so traits. And we'll potentially talk about templated traits later, but you can template your traits. Anyways, so how do we end up writing code that we see in stuff like vector and hash map and that sort? So we know what a normal struct looks like. We have our struct declaration, the type name, and then any data inside. Any functions that we have, go in this little impl block, and they can return any sort of data. So to make that generic, when declaring our type, we use our angle brackets, and we have this type variable t. Again, t can be anything you want. T is a sort of convention I've seen used, but it is not really, it's not a hard and fast rule. Name your type parameters whatever makes sense in the context of your code. So in this case, we're creating a generic value struct that holds one value of type t. And so then when we implement functions on that, we are implementing functions for the type t on our generic value of type t. So the biggest difference here is angle brackets after the type name, angle brackets after your impl, and again, angle brackets after the type name. And then once you do that, you can use this variable t throughout your code. This function, it returns a reference to whatever is inside our instance of the struct. And then you can use them just like you've been using any other generic types in the Rust standard library. You just simply declare your type as a type name and in angle brackets whatever the generic type is. And you have this sort of replicated struct over multiple different type parameters. So we can make a generic value of integers, a generic value of strings, or a generic value of floats. And yeah, they all have the value function associated with them. Let me hide my camera. You get access, well, rather, all of these types have this .value function. So if you just call this print function, you'll see 3, then 3 again as an integer, ABC, and then finally 3.0. So you get this duplicated code all by making your type generic. Okay, so let's write our own option enum. We now know how to do so. We have all the pieces. We have the generics. We know how enums work, and we know how match statements work. So let's take a crack at implementing our own option and writing some functions on that. Okay, so we know option takes two values. It takes sum, and there's something inside the sum case, or none with nothing inside. Okay, and we know we want to make our option generic because that's how the standard library implements it. So we'll use our type parameter in here. I'm just gonna, let's see. I'm gonna make this s just to show it doesn't have to always be t. This is quite literally a variable, so it doesn't matter what goes in here as long as it's consistent. So we have our variable s here represents some generic type. We know sum has a single value inside, so we specify that by putting s here. Sum has whatever our option is defined to be inside of it. Okay? And then we said in the previous example, or previous slide rather, we have this angle brackets s after both the impl and the type. And this allows us to use s wherever we like throughout our code. So we have just three basic functions. So unwrap, as you might know, this basically tries to get the value inside sum and panics otherwise. Is sum just returns true if our enum is sum. Is none does the opposite. It returns true if our enum is none. So we can simply just invert that. The opposite of is sum. Okay. So I have this little fill in the blank here. Again, our type parameter, our generic type is s, so we're free to use it wherever we want. So unwrap returns a reference to s. Okay. I believe in the actual standard library, unwrap is one of those functions that consumes self. So I believe the signature looks like this, but for our purposes, we'll keep it as a reference. Okay. So we have two cases, sum and none, and like always when we see an enum, we can use a match. So match self, and there are two cases, my option and sum with something inside, or a none. And so if it's sum, there's some value x inside, we can return a reference to x. If it's none, we want to panic. So panic. There we go. I believe the standard library code is a bit more complicated than this because it shows you, it gives you some more debug information on what happened. This is super generic. Our code will just tell you panicked on a none or unwrap on a none. But this is the general principle. You basically have this type signature that has s. S is your generic type variable, and you can use it throughout your code. Again, same thing with is sum. We can just copy this code over. We don't care what's inside the sum. We just want to return true. And similarly, we don't care about the none. We just want to return false. There we go. And so now that we've implemented this, we basically have access to all kinds of generic my options. So my option of string, my option of int u8. So we can go ahead and run this. There we go. So for the first case, we're checking if it is sum. If it is sum, we unwrap that. That's okay because it is sum. On this empty case, we start out with none. We found an empty option, and we tried to unwrap it anyways. And like we said, it panicked. So, yeah, that's just basic type generics. We can take a look at the standard library, actually. This is a neat trick I like to use when writing my own Rust code. So you can't really see it, but if you right-click on this actual sum here, it will give you an option to open up the source code. So go to definition. And here we go. We have the actual Rust standard library implementation of option. Enum option, this pub just exports it. We'll cover sort of exporting functions and all in a little bit, but and these are just some macros to sort of define any metadata and whatnot. And again, impl t on the option type gives you this access to a generic parameter t, and you can use that throughout your code. Here we go. Is sum and they use this parameter t that takes, this implies a function that takes in a type t. Let's see. Again, using option and t here. So generics are just super powerful tool that gives you options to make your type generic, help you reduce code duplication and all that. So I strongly recommend you take advantage of it if you're implementing your own container, if you're implementing something that can be sort of made generic. Yeah. Okay. So now on to smart pointers. So pointers are this general concepts for variables that contain an address in memory. We talked about fat pointers when talking about references and slices. Fat pointers are just an address with a length associated with it. So pointers are this general concept for variables that have an address to memory. Smart pointers are data structures that not only act like a pointer, but also have this additional metadata and really powerful capabilities. So you're probably already familiar with them. Strings and vectors are themselves smart pointers. They have a pointer to some character or some type array in memory, and they have some information about the length, the capacity, whatnot. So you've already worked with them before. Now we're going to take a look at how they will look under the hood. So string and vector, they're smart pointers. They manage their own memory. So when you drop a variable of type string, all that data on the heap is freed up. Same thing with vector, and you're able to sort of reclaim that memory under the hood. So smart pointers take ownership of the data that they point to. And so when the variable that owns the smart pointer goes out of scope, the data that the smart pointer points to is also dropped. So when your smart pointer structure is out of scope, data is dropped. Okay, so this is a super basic smart pointer in Rust. It's called the box. So boxes allow you to store data on the heap rather than the stack. When you declare a box, your pointer is on the stack, but the data that it points to is on the heap. So be careful with that distinction. The actual pointer itself, the memory address, that gets stored on the stack. The actual memory address, the contents of where that memory address is on the heap. So a pointer to heap data is on the stack, and when this box smart pointer goes out of scope, the data on the heap is freed. So what does that look like? When we initialize a new box, we have this box here. It contains a little pointer, this memory address. That memory address is located somewhere in your heap. So we have some data, it's put on the heap, and we have a pointer to that data. Okay, so how do we use boxes? No? Okay. How do we use boxes in Rust? So you create a new box pointer, smart pointer, using the : new constructor. It takes ownership of the data you pass inside, and it puts it on the heap. So make the box variable mutable if you wish to modify the underlying data of the box. So if your box smart pointer is not mutable, the data inside is also not mutable. And then if you want to sort of get access to the data that the box points to, you can dereference it. But the same dereference rules apply. If you're using square brackets on a vector, you do not need a dereference. If you're calling a function on this smart pointer, you do not need a dereference. You only need a dereference when you're sort of accessing that data specifically. So you're not using a function, you're using an equal sign to change the piece of data directly. So this sort of automatic dereferencing that you encountered in the past homeworks, this also plays in here. Same rules apply. So be careful. Okay, so let's take a look at boxes. You can simply declare a box with box new. It takes ownership of this string, and then we have our mutable smart pointer to a string. Again, it's a generic type. It's a smart pointer to some type. Type is generic. And so if you want to modify B, you don't need a dereference at all. You can simply use B like it is a string. You can call push string on it. You can print it out. But if you want to change the underlying data, then you have to dereference. So we're not sort of modifying this data. We're actually changing the contents of the entire space of data. So hence this dereference. Okay. If we run this, we get CS128 honors, and if we change it, we get hello there. So dereferencing rules apply. The same would apply if this was a vector. Square brackets, you do not need to dereference. Okay. So the biggest place you'll be using this in this class is with linked lists. So let's talk about why. So you use boxes when you have this type where you don't know the size at compile time, and you want to use this value in a context that requires an exact size. So when you're defining your own struct, Rust needs to know the exact size of every single piece of data in your struct, so that it is able to sort of allocate and deallocate structures efficiently, properly, guaranteeing this memory safety. So when you don't have a type that has an exact size, use a box if you want to put it into a struct. And I'll show you what this not having an exact size means in a couple slides. So boxes are also used when you want to own a value and you only care that it implements a particular trait. So if all you care about is that some type has some particular behavior, you can declare it as a box that contains some type implementing a trait. You'll see this a lot in error handling. You'll see box and then dyn error. This is sort of meant to grab any kind of error that might arise and just stick it on the heap so you can get access to it later. Again, we'll cover this with traits because this plays directly into using traits. Okay. So this is what we mean by not knowing the size of your type. So we have this seemingly innocuous linked list implementation. Linked lists are simply this little link, and then they have a pointer to the next piece of data in your list. So again, another link and a pointer to the next piece of data. We don't have any guarantees that these are contiguous in memory. They can be all over the place. There are some implementations that have links going backwards. So this link might have a link going backwards. That's very, very difficult to implement in Rust. We don't expect you to do that, but you should have seen this in CS124. And then the front piece of data is called the head. The last piece of data is called the tail. We don't have a tail in this implementation, but it exists. So this is some way we can implement this in Rust. So we're creating a generic struct. Each link has some piece of data t. Don't care what it is. Could be an integer, string, whatever. And then we have this next pointer. So next is either some and it's another link, or none and it's no link and it's the end of our linked list. But there's an issue in Rust. This is what's known as a recursive type. So a link contains another link, and this link could potentially contain another link and then another link. And so you never know how many links are contained in this, hence the infinite type. And so Rust actually generates a compiler error for you on this. So this recursive type has infinite size. You have no guarantee as to how many links are going on here. You could have another link, and so on. So this is the case where we want a guarantee as to the size of our type. So we can put our recursive link into a box. So now every link has a smart pointer, so pointer to a piece of data on the heap, and then this next link is somewhere on the heap. So it's not a link inside another link inside another link, like we had here, it's links on the heap and pointers to those links. So this is the implementation you'll be using on homework 8. And we'll talk about how to write functions over these. But all you need to know is why we need boxes, how they play into recursive types, and we'll talk about how to use them in the next lecture. That's all, folks. Thanks for hanging in there. Take care.